In this first course, I will give a short introduction to vector and matrices. So vector and matrices are two very useful tools of linear algebra. First, before talking about linear algebra, I will introduce just a reminder of what is a linear physical system. So you have a system here, and then in this system you have some input and output. So this system can be complicated or not. So if for an input I1 we have an output O2, in parallel, if for an input I2 we have an output O2, then if we have the input I1 plus I2, then we have the output O1 plus O2. So this is called the additivity property. And for your system to be linear, you need the second property, which is multiplication or scaling, which means that if you multiply your input by some constant lambda, then the output is multiplied by the same constant. So when these two properties are satisfied, linearity and scaling or multiplication, then your system is said to be physically linear. So several examples of linearity. The first one is that Earth is flat. So we know that when we are just on the ground looking to the Earth, we can imagine that it is flat. We know that it's not wrong, but linearity is often the first approximation on physical system. This is what is called small perturbation here. Yes, so it's fact the curvature for small scale. Second example is more linked to what we know. This is for a mass spring system. The restoring force in the spring is a linear function of the displacement of the spring. So this we can use this example to define and to represent physical system by list and arrays of numbers. So let's consider this example. So we have here two spring, here some mass. In fact, the fact that this mass has no point right now, and these two mass, what is important is that they have two displacements, x1 and x2. And then we will consider the restoring force in the spring, so the first spring here and the second spring. And then we will write the restoring force as function of the displacement x1 and x2. It's very common that F1 is equal to minus K1 X1. So it means that the restoring force in this spring depends on the stiffness of the spring and just the displacement X1. So this is the elongation of the spring. And then we can see that F1 doesn't depend on X2. For F2, we have a similar relation, except that this is the stiffness K2, and then the elongation is X2 minus X1. So we have the two relation that gives the input x1 and x2 and the output f1 and f2. So we have two relations and we can rewrite in a single relation by first doing some rewriting. So we can write like that, f1, f2 minus k1 x1 plus 0 times x2 because there is no dependence on x2, and k2 times x1 minus k2 times x2. So we see here that we have ordered the things. Here my two outputs, here my first input, my second input. And then we can write this as a single relation by defining merging f1 and f2 in a vector called f. So this is a list of two numbers. The same for the displacement. And then the relation between the displacement and force can be rewritten with an array here with the four numbers, two lines and two columns in my array. This array is called a matrix. And I know that when I see a relation like that, that it means this relation, which is equivalent to this one. So this can be generalized, and more generally, we can write that the output can be written as a matrix here, where we have put some generic coefficient. Okay, so when we obtain the input as a function, the output as a function of the input, this is called a direct problem. And when we know the output and then we want to know the input, this means that suppose that we know the restoring force in the spring and we want to determine the displacement, then we need to do an inverse problem. So the inverse problem is not always solvable, and we will come back to that later on. Of course, this is here a rewriting of the relation f1, f2, the matrix, the coefficient x1, x2. So let's now have a more complete definition of vector and matrices. So a vector is an ordered finite of scalars. So the scalars are the numbers, scalar in another way to call numbers. These scalars here are real, but we will see later on that they can be complex. So this is an ordered list, and what is important is that it's ordered and finite. The scalars are called the component of the vector, and Rn is the set of all the vector of real number with a list of length n. Just a few examples, or just some small comments, is that for two vectors, it's important that they are ordered. So these two vectors are not the same, and also they should have the same dimension. And here, it's not because you have a 0 that this is the same vector. We have seen that we have two properties for linearity. So we can see what happens when we want to add two vectors, so to generalize the addition. So if we have two vectors x and y, then the sum of x and y is the sum where all the components are the sum of the individual components. So x1 plus y1, xi plus yi, until xn plus yn. We can also multiply a vector by a scalar number. In this case, I have my scalar number here, lambda, and x is my initial vector, and we see that the product of x by lambda, I just multiply all the components by my scalar number lambda. So for matrices, this is arrays of number, same thing. One coefficient in the matrix is called the entry, and the entry has an index for line and column, y and j here, which are in the good range. And a matrix, we have seen formally arrays with just 2 lines and 2 columns, but the number of lines can be n and the number of columns can be m. N and m are not necessarily the same. And a matrix is a square if n is equal to m, and is yes, skinny if the number of lines is higher than the number of columns, and fat if the number of lines is lower than the number of columns. Just to say that the scalars are real number in all the things that I said before. They can be also complex number, and this can be generalized to complex number. So we have seen this input-output relation. So let's see how we can generalize this matrix vector multiplication. So this is what we have seen before. So here I have a first vector x, and then this first vector has m component, and then the output has not necessarily the same number of components. We see that this n, and this n can be equal, but it can be also different to n. And then in this case, the matrix should have n rows or n lines and m columns. So the number of columns of the matrix is equal to the length of the input, and the number of column of lines is equal to the length of the output. Okay, and then we have the dedicated calculus, which is the generalization of the sum that we have seen previously. We have seen matrix vector multiplication, but we can also multiply matrix altogether. This is just by seeing that, in fact, a matrix is just a collection of column vector that are put together. So in this case, this is the generalization of the matrix vector multiplication. In fact, this generalization is done by, here we see the first column, and here we have the first column of the output matrix, and then based by that we can multiply and have correspondence between all the columns. Okay, so this is the generalization of matrix vector multiplication to matrix-matrix multiplication. And then we have to notice that there is some requirement. And the main requirement is that if we want to multiply a matrix M and a matrix X, then there is a necessary condition, which is that the number of columns of M is equal to the number of lines of X. And then the result, we can see here that the result, the number of lines of the output Y is the number of line of M, and the number of column of Y is equal to the number of column of X. Okay, so after we can generalize the formula that we have seen before, and it's important that you mention, we will do some exercise, but it's important that you check that when you make the multiplication of two matrices M and X, that the condition on the dimension is fulfilled. And after, when this condition is fulfilled, after, the dimension of the output will depend on the two other dimensions, number of line of M and number of column of X. So take care about the dimensions. So let's now see some application of matrix and how can matrix can be useful. So for example, I come back to a similar system when I have three springs and two masses, or two displacement, because this is masses, but in fact mass is not interesting for this example. So restoring force, so three springs, the stiffness are K1, K2, K3, restoring force F1, F2, F3, displacement are X1 and X2, and we can similarly have the elongation of the spring. Then the total length of the spring is the initial length of the spring plus the elongation. So if we see now what can be the relation between all these quantities. So we have a first relation, which is that we have some relation between the restoring force and the elongation. So F1 is equal to minus K1 E1, and the same for F2 and F3. So we can use matrix to represent the relation between force and elongation, and we can see that we have a very simple matrix. This matrix is called diagonal. We will see that later on. So this is the first relation, and we have also some other relation, and one relation can be to relate displacement to elongation. So elongation E1 is just x1, elongation E3 is minus x2, because when x2 is positive, E3 is negative, and elongation E2 is equal to x2 minus x1. And then this can be put in some other matrix. So E1, E2, E3, three elongation, two displacement. My matrix has three lines and two columns. Here we see that the number of columns is equal to the number of components of X. And then if I want to obtain F1, F2, F3 as a function of X1, X2, X2, well, X1, X2, I just have to make successively the two products, and then F1, F2 is my first matrix multiplied by E1, E2, E3, and I replace by this relation. And then here we have the multiplication of two matrices. And then when we make this matrix multiplication, we have that F1, F2, F3 is a matrix with three lines and two columns times X1, X2. And then F1 is equal to minus K1, X1. F2 is equal to K2 times X2 minus X1. And F3 is equal to minus K3, X2. And then this relation that we can obtain previously, and it's not very difficult, in fact, to obtain this relation, but we have seen here that it can be obtained by matrix multiplication. And this is an interest of that. And Let's now consider the system which is a bit more different, but at least we will see that we can use the matrix-matrix multiplication. So here we have a duct with, in fact, two ducts, and here there is a junction, and the diameter of the ducts is not the same. So let's suppose that we are under some plane wave assumption. Then, in fact, the physics on one line is in fact just given by two numbers, which are pressure and velocity. So we can put this pressure and velocity in the same vector. And in fact, for each abscissa, we have one value of pressure velocity. This vector is called the state vector in physics. We will come back to that later on. And then if we write the physics, the idea is to write the relation between P2 V2 and P1 V1. And for that, there is, as this is a linear system, we have a concept which is, or a kind of matrix, which is called the transfer matrix, which can give the relation between P2 V2 and P1 V1. And the same for the junction linking P3 V3 to P2 V2, and after linking P4 V4 to P3 V3 in the second duct. So in fact, we can introduce this free transfer matrix, one T1 for the first duct, T2 for the junction, and T3 for the second duct. And all these matrices have two input and two output, so there are 2 by 2 matrices. So now, if we want to obtain the relation between P1 V1 and P4 V4, or if we want to obtain P4 V4 as a function of P1 V1, then in fact we just have to multiply the matrix. So when I have P1 T1 times P1 V1, this is P2 V2, multiplied by P2 V2, I have P3 V3, multiplied by T3, I have P4 V4. So we can see that we can directly have the relation which gives us P4 V4 as a function of P1 V1. And then this matrix is 2 by 2. So we obtain directly by multiplicating the matrix. So it was a short introduction on matrices. This was to introduce you the concept of matrices and vectors, and to see that physical system can be represented by a list and arrays of numbers. We have a dedicated arithmetics, especially linking about dealing with the product of matrices. And this is a very common tool to express linear relation or linear physics by numbers that can be used in some computers or some programming language, and then to represent physics in a very close form. Thank you for your attention.